Basic physics of MRI scanner. Hydrogen atom. Plus. Nucleus. Electron. Proton. K-shell. Net magnetization vector. The sum effect of all magnetic moments for a given sample. Represented by the symbol m. mz. Alignment / precession. Terminology. B0, the symbol used for the static magnetic field. Hertz, a standard unit of measurement for frequency, measured in cycles per second. 1 Hertz equals 1 cycle per second. Phase, a position in time along a rotation. Precessional frequency. Lower B0. Asterisk changes proportionally to B0 changes. Higher B0. A spin or wobble that is caused by the static magnetic field. The protons spin or wobble in a circular path about B0. Larmor equation. W equals G-Bo. Precessional. Frequency. Hydrogen. 42.6 MHz. Magnet. Field strength. Precessional frequency chart. Isotope 0.20.51.01.5. 1H. Resonance. Terminology. B1, a magnetic field introduced perpendicular to the external magnetic field, B0. Frequency, number of crests or cycles per time period. In Mr. This magnetic field is produced by an electromagnetic wave at a particular radio frequency. Radio frequency. 2 conditions must be met before resonance can take place. 1. The RF must be introduced perpendicular to B0. 2. The frequency of the RF must match the precessional frequency of the nuclei. Mr. Signal generation. FID, an abbreviation for free induction decay, which is the measurable Mr. signal that is induced in the receiver coil after the RF transmission is terminated. Free precession, the absence of a driving RF force. Free induction decay. FID. MR signal. Alternating current in the receiver coil. Decaying signal of transverse magnetization. Free precession. 3 phenomena occur when RF is terminated. 1. Nuclei emit energy and shift from a high to low energy state. 2. Magnetization returns to longitudinal plane. 3. As transverse magnetization decays, nuclei get out of phase with one another. 4. Mr. signal is generated. RF present, RF absent. Magnet bore. B. O. Current carrying coils designed to produce a desired gradient magnetic field which changes strength in a given direction. Gradients. Spin echo PSD. RF. GZ. GY. GX. 90. 180. 4. Gradients. Speed up or slow down the precessional frequency of spins caused by slight changes in the magnetic field strength. Used to select a region for imaging and to encode the location of signals being received. Slice selection changes the magnetic field, which will result in changes in precessional frequency. When RF is transmitted at resonant frequency, magnetization is created in the transverse plane. Prior to phase encode, phase encode, post phase encode, phase encoding. K-space. High amplitude, gradient, low amplitude, gradient, edge detail, outer edges of K-space, highest senior, middle of K-space, K-space / gradient amplitude. Phase encoding. Maximum positive amplitudes, minimum positive amplitudes, minimum negative amplitudes, maximum negative amplitudes. 19. Frequency encoding. Frequency. Spatial encoding. 25. Gradient slope. Both the FOV and the slice thickness affect the gradient slope. A steeper slope results when the gradients have more current flowing through them. More current results in more heat. Smaller FOVs, thinner slices, and higher matrix values stress the gradient system. 7. Fourier transform. Used to reconstruct an image from the set of encoded MI signals. It changes the signal from a frequency / time domain to a frequency / amplitude domain. 26. Spin echo PSD. RF. GZ. GY. GX. 90. 180. 4. 2D multiplanar. Acquiring multiple images within a single acquisition or time frame means that the order of slice excitation is odd-numbered first, then even-numbered images. All slices are acquired within the TR period. Multiplanar acquisition. All 5 slices in the same TR. 1, 2, 3, 4. Crosstalk. Slice interval or gap is the distance between each slice measured from the center of one slice to the center of the next slice. Crosstalk occurs when protons bordering a slice become excited during slice excitation. As a result of this cross-excitation, the transverse magnetization is saturated when the protons in the bordering slice are excited. There is a senior and contrast loss resulting from crosstalk. 10. Crosstalk. 2 ways to minimize crosstalk. 1. Multiple acquisitions. Order of excitation. 2. Use an interscan spacing. Order of excitation. S. L. I. C. E. 1. S. 2D sequential. Acquiring an image sequentially means that all the excitation pulses, hash of phase steps x next xtr, are delivered for one location before the process is repeated at another location. Sequential acquisition. 1. Each slice is completed before moving on to the next slice. 5. 3D acquisition. In volume or 3D imaging, A wide RF pulse is delivered to excite an entire scan volume or slab. Spatial encoding must then be done in the phase, frequency and slice axes. 3D volume, slice, encoding, phase, encoding, frequency, encoding. 6. 3D acquisition, 3D slab. 7. Spatial resolution. How close two objects can be before they can be distinguished as separate objects. 11. Spatial resolution. 3 parameters affect spatial resolution. FOV, matrix, slice thickness. Small FOVs, large matrices and small slice thickness result in high spatial resolution. Column, row, voxel. FOV. FOV determines the amount of anatomy displayed on the image. The larger the FOV, the larger the pixel size, and therefore the resolution is decreased. FOV can be changed in 1 cm intervals. 24 cm FOV, 16 cm FOV. Signal-to-noise ratio. Senior is the ratio of the amplitude of the MR signal to the amplitude of the noise. Noise is the undesirable signal that is generated from the patient, the environment and the system electronics. 17. Signal-to-noise ratio. Exception to rule, receive bandwidth. Senior, plus 32 kHz, plus 16 kHz. Noise, signal, X gradient, plus 16 kHz. Receive bandwidth. TR, readout window, X gradient, plus 32 kHz. TR. Receive bandwidth trade-offs. Chemical shift equals frequency difference between protons bound in fat versus water. Fat. Contrast weighting. Images are labeled according to the internal factors predominantly responsible for the variations in signal intensities. The goal in MR is to select a pulse sequence and timing parameters that will cause one of the 3 contrast mechanisms to predominate over the other 2. 26. Contrast weighting. T1 weighted images result when the variation in longitudinal regrowth creates transverse magnetization differences which predominate over other contrast mechanisms. T2 weighted images result when the rate of nuclear dephasing predominates over the other contrast mechanisms. Proton density weighted images result when the number of nuclei in a tissue is predominantly responsible for the image contrast. T1 relaxation. T1 relaxation. Longitudinal recovery. Spin lattice energy exchange. 28. Saturation. TR and flip angle control saturation which controls T1 effects. 30. T1 relaxation. Factors that affect T1 relaxation rates. Field strength. Lower field strength equals faster recovery. Higher field strength equals slower recovery. Tissue lattice. Firm lattice equals faster recovery. Loose lattice equals slower recovery. T2 relaxation. T2 relaxation. Transverse relaxation. Spin-spin effect. 30. Dephasing. S. I. G. N. O. L. 1 T2 2 T2 3 T2 4 T2 5 T2. Time, 10. 37%. 16%. 5%. 2%. 0%. T controls dephasing, which controls T2 effects. Spin density, hydrogen content, mobility of hydrogen. Field strength affects the number of hydrogen protons that are parallel with both. 34. Tissue contrast. Relaxation recovery, T1. The time it takes the net magnetization to return to B0. Relaxation dephasing, T2. The time it takes the protons to dephase and thus for the net vector to decay. Nuclear density, PD. The number of nuclei that comprise the vectors from various tissues. Scan timing parameter chart. TR, T1. TET, T2. Tissue intensities. For the brain. White / gray equals grayer. CSF equals brighter as TET. Fat equals dark, bright, FSE. White, slice. Thickness. Nex. TET. TR. FOV. Receive. Bandwidth. Senior. SP res. Time. Cont. T1. PD. T2. Contrast is directly affected by TR, TET, T, and flip angle. Senior changes can enhance or obscure contrast but cannot change the image weighting from one type of contrast to another. T2. Inversion recovery. RF. GY. Echo. 90. 180. 3. 180. T ranges. 25. Dual echo. RF. GY. Echo. 90. 180. 180. A dual or multiple echo sequence looks like this. 3. Dual echo spin echo. Time. S. I. G. N. Fast spin echo. ETL equals 8F. TEL equals 5x ESP. GY. GX. Echo. RF. 9. Echo train length. The number of echoes selected by the operator in the FSE sequence. It is annotated ET on the image. 14. First TR. 8 ETL. K, space. Time. S. I. G. N. Echo space. Echo spacing is a multiple of the minimum TET. Scan parameters that increase min TET. FOV. Min TET. Min TET. Min TET. Min TET. Echo train length. How ET. 16 echoes. 16 echoes. 16 echoes. Scan time for spin echo. Example, 2256, 2, 1/60,000. Acquisition time equals TR, hash phase encodes, nex, 1/60,000. 2. Scan time for fast spin echo. Example, 2256/16, 2, 1/60,000. Acquisition time equals TR, hash phase encodes, nex, 1/60,000. ETL. Receive bandwidth. Receive bandwidth has an effect on many factors in FSE. Here's what happens to these factors when we increase the RBW. Min TET. Gradient echo PSD. RF. GZ. GY. GX. 29. Comparison. Spin echo vs gradient echo. Similarities. Both use an RF excitation pulse. Both use gradients for slice selection, phase encoding and frequency encoding. Both generate an echo. Differences. A spin echo uses a 1800 RF pulse to refocus vectors, a gradient echo uses gradient reversal to refocus vectors. The 1800 RF refocusing pulse will correct for T2, T2' effects. The refocusing gradients will not be able to correct for T2 effects. Comparison. Spin echo vs gradient echo. 31. T2 asterisk. The sum of T2 and T2 effects that influence transverse decay. 1/T2 plus 1/T2 equals 1/T2 asterisk. T2 is the transverse decay due to magnetic field inhomogeneities, chemical shift of the second kind and patient-induced magnetic susceptibilities. Contrast weighting. T2 asterisk weighted images result when the rate of transverse magnetization decay due to local field inhomogeneities predominates over other contrast mechanisms. What causes the magnetic susceptibility artifact? Various tissues magnetize differently in a magnetic field. It depends on surrounding conditions. One tissue will magnetize to a great degree, where another will not. We see these great differences at air/water interfaces. These tissues' precessional differences set off a local field gradient that causes a lot of dephasing. This is a T2 effect that gradient echoes do not correct for, so that local gradient causes dephasing in those tissues. That is why we get signal drop-off at the air/water interface. One example of an air/water interface is around the sinuses. In phase. Out of phase. Chemical shift of the second kind. Chemical shift of the second kind. Transverse steady state. Tissues with a long T2 relaxation time will have more residual transverse magnetization, larger transverse steady states, than those tissues with short T2 relaxation times. This is because tissues with longer T2 times will remain in the transverse plane for a longer time period before the signal begins to decay away. 2 ways to eliminate residual transverse magnetization. 1 time, this allows the residual transverse magnetization to normally decay, resulting in the loss of signal of contributing tissues. 2 spoiling, RF spoiling or gradient spoiling. This prevents build-up of magnetization in the transverse plane, therefore no steady-state contributions. 2 DGRE. Multiplanar gradient recalled echo. The longer TR and a killer gradient pulse minimize residual transverse magnetization. The TR should be 200 ms or longer. 2 DGRE. Use a TR, 200 with a short tear. Short flip angle, 200, this will give good T2 asterisk contrast. The longer TR will allow for little saturation, so we do not see much T1 influence. SPGR. Spoiled gradient recalled echo. The RF excitation pulse is phase shifted each time the RF is applied, which prevents accumulation of the residual transverse magnetization effects throughout the acquisition. This reduces the T2 effects. Combine this with a short tear to reduce T2 effects, and T1 effects will predominate the image contrast. SPGR. Using a short TR and a short tear with moderate flip angle, 450-600, here we get the best T1 weighting.
Increased saturation of the spins contributes to the T1 influence, while RF spoiling prevents a great deal of T2 * effects. Thank you.